Bismillahirrahmanirrahim. Okay, so now let's discuss IP addressing. And the agenda of this topic is to first of all understand the basic structure of IP addresses, how they were initially introduced, and what happened over the years when the active internet users have greatly increased, and how have we been coping with the growing demand of internet users till today, and eventually how will we will be dealing with IPv6 when the time comes. So first of all, IP addressing IP stands for Internet Protocol. Basically, it is corresponds to the unique identification of an active internet user. So basically, you have to have an IP address to be able to be found over the internet. If you're not able to, if you're not capable of being found over the internet, no traffic will be able to reach you over this public network. So the basic structure of IP address the basic structure that we start IP addressing began with was IPv4, and we're still currently using IPv4. And IPv4 means that the whole addresses are 4 bytes, and the bytes, individual bytes, are separated by these dots, and this representation that you can see here is an example of IP address, and this is known as the dotted decimal representation. So why is it called dotted decimal? Because of course everything has to be converted into binary, but for your documentation, for humans to be able to understand this, a common representation of IP address is known as the dotted decimal. Each decimal number is represented by, is separated by dots, and we got 4 numbers here. So basically this is 1 byte each. The limit of each group or each number should be up to 255, as mentioned earlier. So it's 1 byte, 1 byte, 1 byte, ranging from 0 to 255. And that does not mean that these numbers cannot be represented in hexadecimal. They can be. But even in hexadecimal, individual bytes have to be separated by these dots. Now, with 4 bytes, that means we have 32 bits, and that's a total of 4 billion IP addresses. Now, since the world population, if I'm not wrong, is around 7 billion now, and several people are making use of 2 IP addresses at the same time. So, for example, you're sitting on your computer as well as you have an active internet connection on your phone. So basically, we got a lot more active internet users than the active population as well. So that means that these 4 billion IP addresses are not enough, and the time when they were introduced, at that time 4 billion IP addresses was more than sufficient, because there weren't that many people who had computers, and they weren't active internet users back then. But now, since we have a lot of active internet users, a lot of computers, even we got non-computing devices such as air conditioners and other household items that are capable of connecting to the internet. Now, with such wide variety of devices being currently used now, these 4 billion IP addresses seem awfully short. Now, how have we progressed over the years with respect to different techniques, making the most of out of these 4 billion IP addresses? We'll be looking into those. First of all, let's understand the basic structure of IP addresses. Each IP address is made up of 2 parts. That is the net ID, which is used for identifying the individual network. Similarly, we got the host ID, which is used to identify the individual device on that network. So basically, if some traffic is to reach you, it means that first of all, that packet, for example, that packet will first have to reach your network. Then after it has reached your network, then only then it will progress towards the you connected on the network. So first of all, you have to, the net ID will be identified. Then from that network, you will be traced on that network. So this is the sequence of events that take place with respect to identifying you over the network. Now, obviously, since IP address is divided into 2 parts, the net ID and host ID have to be able to, be distinguished for interconnecting devices. Now, this is a problem because overall IP address, for example, a router in between, this is what it looks like, minus the spaces. The spaces is just for your understanding, but basically your IP address just looks like a sequence of ones and zeros to a router. Now, if my router is not capable of identifying what part of this IP address is the net ID and what part is the host ID, how will it be able to identify your network and then thereby identify you? So for it to accurately reach you on the network, it has to be capable of identifying the network and then thereby identifying the host on that network. So a scheme was introduced to be create a clarity with respect to the net ID and host ID distinguishing on an IP address. And this scheme was introduced three classes of IP addresses. The class A looks like this: that the most significant bit is always going to be zero. This is the identifying bit that is used for interconnecting devices to know what class of IP address is being used. So if they see a most significant bit as a zero, then they know it's a class A. Now, what does it mean for a class A? For if a class A IP address is being used, then the device will know that exactly 7 bits are reserved for the net ID. So if it sees a sequence of ones and zeros like this, it will know that the first 7 bits after the first zero, the remaining 7 bits are the net ID, and the following 24 bits are the host ID. So this separation allows for a clear distinction of what the net ID is, what the host ID is. Now, this allows for a very small number of networks because there's only 2 raised power 7, 128 networks allowed in this setup, whereas each network is allowing 2 raised power 24, which is millions of different hosts maybe. So this is a huge, difference between the networks and hosts, and this, you know, it's beneficial for large organizations, but not all organizations capable of having, this many hosts connected to it. So it has more hosts versus networks. However, if you want to create a little more networks, class B can be used. Class B means that I've got 10 as my identifying bit. First 2 bits are used for identifying what class it is. After the 10, my interconnecting devices will be knowing that since it's class B, the remaining 14 bits that come after this are the net ID, and followed by 16 bits for the host ID. So this setup allows for clear distinction between the net ID and host ID. Now again, this allows for 2 to the power 14 networks, which is an improvement on the class A, but not that much. However, if you look at class C allows for 110, as the 3 bits for identifying. So if once the router is capable of seeing a 110 at the beginning, it will know that the remaining 21 bits are that follow after the first 3 bits identifying bits are the net ID, and followed by 8 bits for each host ID. So that means I'm allowed 2 to the power 21 different networks, and each network is allowing 256 hosts. So this, you can see that this setup allows for more networks. This is allowing for each network having 256 hosts. So in this particular setup, you're supporting large number of networks, and each network with 256 hosts. So this seems like a better, more commonly used approach. Now, the problem is that it is possible that you may want to, adjust the number of bits for your net ID versus host ID based on your requirements. So for example, I may want to adjust the number of bits to add a little less number of, hosts. I don't want to go all the way. Let's say I want to add 18 bits for the net ID and the remaining, 10 bits for the host ID. I can do that. I can, I may want to, shuffle these bits around with respect to how many networks or hosts I need at that particular moment. Now, if I'm sticking to these classes, they won't allow the net ID versus host ID separations apart from these. You have to follow any one of these models. So if you want to go for, say, an 18 to 11 bits, for example, 18 to 11 bits, you don't have, that particular option in these classes. And basically what that means is that if you want to support such, kind of setup that allows for, say, 21 bits or maybe 20 bits for the net ID and the remaining 12 bits for the host ID, such kind of setup is not allowed in any one of these classes. So basically what happened here is that you went classless. Now, if you weren't going classless, we're coming back to that problem again, that if I've gone classless, what part is the net ID, what part is the host ID? Now my interconnecting devices will again be confused as to what part will be of these 32 bits will be referred as to net ID and the host ID. And thereby, if it's not capable of identifying the network, it will not be capable of identifying you on that network either. So if you have gone classless, that means that you are not following any one of these arrangements. You're going on a separate way, and probably that's your requirement for that. If that's your network's requirement for that particular moment, and if you've gone classless, that means my interconnecting devices will not be able to distinguish between the net ID versus host ID bits, and therefore it will not be able to properly identify you on a network. Now, the reason that you may want to do this because requirements may be other than these three classes that you have. Now, to avoid this problem of going classless and creating confusion of where you lie on the network, a solution is known as the classless interdomain routing. Now, classless interdomain routing allows you to go to classless, so you don't have to follow any of these one of these bits. So because these classes allow for identifying bits, and thereby each device will know what comes after. So if you have gone classless, that means that there's no way of my interconnecting devices to know what part is net, what part is host. So in that case, a solution interdomain routing, classless interdomain routing presents that instead of having a defined class and a class identifier, what you can do is that if you're using an IP address that does not link with any one of the classes, you can go ahead and add a suffix at the end of your IP address. Now, the suffix simply identifies the number of net ID bits that are reserved in the address that you have just sent. So even if you're not going with any class, that doesn't matter because you have mentioned what parts of this particular IP address is the net ID bits and what part, and of course, the remaining bits will be referred to the host ID. So in this particular address, as you can see here, is that I'm using the 21 bits, the first most significant 21 bits, as this number is 21. This is the suffix. So the first most significant 21 bits will be the net ID, and the remaining will be host ID. So this solves the problem of what part is the net ID, what part is the host ID by adding this suffix. So my interconnecting devices will observe this suffix, separate the net ID bits and the host ID bits, and thereby successfully communicate with you over the internet. So that's one solution. If you don't want to follow any of these classes, you can go classless by using classless interdomain routing. Now, there is another problem here, which is known as another solution, which is known as subnetting. Now, subnetting basically means that uh, if you want to allow for different networks to connect to the internet, you can do that. Okay, just a quick recap. If you remember that the net ID of your IP address is used for identifying the network. So if you want different networks, you will need different net IDs, obviously. Now, subnetting allows us to create different networks without using different net IDs. So this approach allows us for using a lot of different IP addresses by not wasting IP addresses. Subnetting allows us to not waste any IP addresses at all. So basically, if I want to host different networks, I will need different net IDs. Now, if I don't allow for different net IDs, then I won't be able to separate different networks. Now, subnetting allows us a technique that you can, create different networks in your setup, in your organization, without having to, buy or purchase or, take up different net IDs. You can do it by just using one net ID, for example. Now, that is the process of subnetting. Now, to understand this process, let's look at this example. There's this organization that has 150 active users and 150 active users sitting on 150 computers, which are connected to the internet. And all of these 150 computers are divided into seven different networks. So by this logic, for 7 different networks, I will need 7 different net IDs. And since we understand that class C is the most common approach, that means 7 net IDs, and each class C net ID is capable of hosting 256 computers. So each net ID, class C net ID, is capable of holding 256 computers. So since I'm occupying 7, that would mean that I've got 1,792 different IP addresses. So considering how much I need only 150 computers. I'm wasting upwards of 1642 IP addresses. I'm wasting 1642 IP addresses that are not used. I only need 150. And this approach of taking up 7 net IDs to make 7 different LANs and each class C net ID, allowing for 256 computers on each one, makes 1792 IP addresses, whereas I only need 150. And that means 1642 IP addresses are being wasted. Now, to tackle this problem, instead of taking up 7 net IDs for 7 different LANs, I only take up 1 net ID. Now, That means let's just say I just occupy one net ID, and I'm gonna say that I've got this one, say for example 192, or sorry, something like this. Let's do something like 195 12 6 and 14. I've got this one class C net ID. So I'm going to remove this part because the net ID portion is the first bytes, the first 3 bytes only. I'm going to erase this. I don't need this. So I just occupied one class C net ID, and the remaining, this portion will be my host ID as the class C configuration states. The remaining 8 bits will be the host ID, and I just take up one class C net ID, just one class C net ID. Using one class C net ID 195.12.6, I can have a range of IP addresses that go from 195.12.6.0 to 195.12.6.255. So that means that this is a total of 256 IP addresses with all the same net ID. All of them have the same net ID. 195.12.6, 195.12.6, 0 to 255, that's 256 addresses. Now that means I've occupied only 256 IP addresses. And how? But the thing is, in those IP addresses, I'm using the same net ID. So how will I be able to identify the different networks on that IP address? Now, this is where the interesting part begins. So for example, let's just say that my net ID portion is the same. It's not changing. But the only variety, the only variations that we see in these addresses is the host ID portion. And those 8 bits of the host ID portion can be, configured in such a way that, for example, these are my 8 bits of the host ID. The first 3 bits will be used to identify the network, and the remaining 5 bits will be used to identify the host. So for example, this IP address you can see here, this host ID you can see here is actually showing LAN number 3. How? If you just look at this, this is 011, which is deanery 3. So I've got LAN number 3 here, and this is computer number 32. Sorry, workstation number 16. Sorry, this is workstation number 16 on LAN number 32. So this is how, using subnetting, we are capable of identifying individual networks as well as individual computers on this network just by occupying one net ID only. So for example, I've got this host ID written here, and this will go something like, for example, now this is LAN number 1 and computer number 8. As you can see here, this is 1, 2, 4, 8. 8 computer LAN number 1. So if we have this configuration here, my interconnecting router can simply forward these packets to the respective networks based on the first 3 bits of the host ID to identify the network. So let's just quick recap of what happens when I am using, for example, this IP address, or I'm using 195.12.6.0. Now, what happens here? Now, basically, if you look at the host 0, that means 0, 8, 0, 0, 0, 0, 0, 0. So that means 8 zeros can represent this one single 0. 8 zeros can be used to represent this one single deanery 0. So if you represent this one value in a byte, that's 8 zeros. So 8 zeros, as I can show you right here, 8 zeros means LAN number 0 and computer number 0. And that's a perfectly valid computer number. How? LAN number 0 can be the head office. For example, we've got the head office line over here. That could be LAN number 0. And computer number 0 can be probably the boss's computer. So system 0, as we remember in computing that 0 is actually a value. So 0, system number 0, LAN number 0. So this is a perfectly valid, separate IP address for your computer, or for a computer situated in LAN number 0. Now, how this works? Say, for example, I'm communicating or some device outside the network wants to send data to this IP address. Now, based on this IP address, my data transmission will reach this network. So there is no other network on the entire public or the entire internet that has the network ID 195.12.6. This is yours. This is the net ID that you purchased. So there's no other network. There is no other way that that packet will reach any other network because this net ID belongs only to you. So based on the net ID, that transmission from the public network will most definitely reach you because the net ID is yours. Now, once it reaches you, once this packet with this destination IP address reaches you, the router will look at the host ID and it will see, okay, it's 0. That means the first 3 bits mean it's network, it's the head office line, and it will forward it here. And let's just say there's another device here, say possibly another router here or another switch. This second device will look at the remaining 5 bits and identify which computer to forward the packet to. So the router will identify the network based on these first 3 bits, forward the data packet to that network. The network router or the switch or whatever central device over here is will look at the remaining 5 bits and identify the boss's computer and forward the data there. So this is how subnetting works. Now, in subnetting, in this example that we see here, we are still wasting 106 IP addresses because this approach will allow me 256 IP addresses. I only need 150. So there's 106 that are not being used, but that's okay. I mean, it's better than wasting 1642 IP addresses. As if, and this would have happened if we had 7 different net IDs and each net ID had 256 computers, and I will be using 1742 IP addresses. I only need 150, wasting 1642. But this approach, subnetting approach, allows for 256 IP addresses, 150 will be used, and 106 will not be used. And you may need them later on because you got, your company is growing, more people will start joining you, and so on and so forth. So these IP addresses, this buffer might come in handy in the future.